Hello and welcome to the last and this time virtual WCT meeting on cognitive interfaces. My name is Simon and I will quickly introduce you to the WCT project on game-based number learning. In one sentence, we conceive learning environments that are based on games as cognitive interfaces, and we try to find out whether such a learning environment offers any benefits when it comes to the content to be learned. Before we have a look at our studies, let me quickly outline the scopes of the current project. Our question is, can such a specific game-based representational format be advantageous to transport the learning content? From a psychological perspective, we try to address this question on three different levels. The first one is the emotional engagement that may be different when using games for learning. The second one establishes a neuroscientific perspective on the neuronal underpinnings of game-based learning because information from this domain is extremely rare. And as a third level, we look at cognitive aspects of game-based learning because they comprise the main factor of learning processes. To every dimension, I will quickly outline the corresponding studies in the following, but before that we may want to see what the content of our interface is all about. The core task of our game-based learning environment is the so-called number line estimation task. The user needs to accurately indicate the position of a given fraction on a line with 0 and 1 at its endpoints. This is a very common established measure used in different educational settings. The result of this test is usually very predictive for later math achievement and is widely used in paper-pencil format. In this rather simple example, the fraction to be indicated is 1/4. So one would indicate the position around here. In our case, instead of pinpointing with a pen on a line, we have an avatar to do that. And of course, this avatar is part of the narrative. The number line estimation needs to be solved by walking the avatar along this line and let him dig for coins. The more accurate and faster you are, the more coins you earn and you proceed in the levels of the game. We then removed all the game-based elements and created a second version which we call the non-game-based variant. This version is reduced to its bare necessities, but it allows us to directly compare the two environments from which the one is based on games and one is not. The feedback after completing one item, for instance, is very different. In case of positive feedback, the avatar shows positive emotions and the player gets rewarded with bonus coins. In the non-game version, you see a green tick. In case you made a mistake, you get struck by lightning or, respectively, see a red cross. Finally, when you reach the top of the mountain, you immediately see how well you did. Nothing like that is provided in the non-game environment. We used this comparison in our first study designed to evaluate emotions during the interaction with the interface. There is substantial evidence that emotions are inevitably tied to cognitions and the formation of memory representation, and therefore modulate cognitive and in turn learning processes. This could be one of the underlying aspects why game-based environments are successful. So the question is, does a game-based interface induce more emotions than a non-game-based equivalent? To measure emotions, we used emotion recognition based on facial expressions. That means our participants were recorded live on camera while they were playing either the game-based or the non-game-based version. The mere frequency of certain facial expressions already describes a difference between the two groups. Eventually, we could successfully classify which participant interacted with which learning environment based solely on the emotions they showed in their faces with an accuracy around 64%. Moreover, the results from the recognition of facial emotional expression showed good correspondence with traditional paper-pencil instruments used to evaluate affect and emotion. Both measures show more positive as well as more negative emotions. To sum this up, a game-based learning setup leads to notably more emotions than a simply computerized analog, as measured by live facial expressions and post-hoc questionnaire measures. And this is true for positive as well as negative emotions. Additionally, our game-based environment is overall evaluated more positively, for instance, rated as more attractive than the non-game-based version. So emotions could be one of the key aspects of game-based learning. Maybe we can get more information by employing neurofunctional methods like functional magnetic resonance imaging. For that purpose, we modified the interface and enabled the participants to actively play the game from within the scanner. Again, this design compares the two versions of the aforementioned interfaces against each other. To meet the requirements of the fMRI, we had to include a control task where digits are replaced by letter pairs and the correct solution is already indicated. The most interesting time frame in this scanner may be the episode when the player receives feedback on how accurate she or he solved an item, so this is what we had a closer look on. By contrasting feedback episodes from the game-based and their very reduced interface, we found that players clearly showed different neurofunctional indicators of emotional processing. For example, a subcortical core area of emotions, the amygdala, shows heightened activation during feedback in the game rather than the non-game interface. The amygdala is one of the acknowledged core areas involved in emotional processing and is thought to be the integrative center for emotions, emotional behavior, and motivation. The remaining part of the project investigated cognitive aspects with respect to the applicability of the game on target groups outside the intended one. We know from previous studies that the math achievement highly correlates with estimation performance in high school students, the group the game is originally made for. This raises the question of the general applicability of our interface across age, or more specifically, does age affect performance in game, and how do elderly players rate the game in terms of subjective experience? To evaluate these differences, we invited adult participants from a broad age range to play the game for 10 to 15 minutes. At first, we outlined the results regarding how much time our subjects on average needed to solve an item. When we look at the resulting speed-related measure of the estimation task, response times of the older player clearly increased compared to those of the younger player. The same effect was even stronger in a second task of our interface, in which participants needed to compare two fractions and place them in the correct ascending order. Again, older players were much slower than younger ones. In these speed-related performance measures, age was by far the strongest predictor. This is well in line with effects known from cognitive aging, stating that speed-related cognitive resources begin to decline around the middle age. Despite performance aspects, the subjective impression of the game is just as important. However, there was no significant gap in how players of different ages experienced the game. Flow measures, for instance, evaluate the balance between cognitive resources and a given challenge. Our sample showed no signs that this balance may have been compromised with increasing age. User experience ratings also didn't reveal a negative impact of age on subjective ratings, suggesting an equally distributed positive rating pattern. To summarize the project in just a few lines, we were able to track differential emotional processing during the interaction with a game-based and a non-game-based learning environment. This was clearly visible in facial emotion recognition as well as paper-pencil methods. Both showed stronger emotional engagement in positive as well as negative emotions. Even during playing inside the fMRI scanner, which is most likely not the usual gaming and learning situation, we could see, for example, heightened activation of areas critical for emotional processing, such as the amygdala. At the level of cognitive processing, we found that mainly response times are negatively influenced by age. This issue could, however, be resolved by adapting feedback loops or altering reward thresholds to more player-appropriate levels. Regardless of these results, players' subjective experience of the game remains stable even at high ages. We may, towards the end of this presentation, conclude that these results greatly speak for the applicability of our game beyond the original target group and recommends game-based learning as a useful tool to overcome modern and upcoming educational challenges like lifelong learning. Thank you very much for listening, and goodbye.